Hey guys, let's do another electric fields problem. 5-point charges, all with Q equals 7.4 coulombs, are spaced equally along a semicircle with radius 2.2 meters, as shown below. Calculate the electric field at the origin. So this is a little different than the previous problem we encountered where we had a full circle. In that case, every charge had a charge exactly opposite it with the same sign. So the electric fields from the two directions would cancel each other out. Now, although we don't have quite the same level of symmetry in this problem, we do still have symmetry. Remember that a positive charge has electric fields coming out in all directions. Okay, so if we take a look at each point charge here, which has the same magnitude and the same sign, they're all going to have electric fields coming out. So just for my own sake, I'm going to label these charges 1, 2, 3, 4, and 5. Okay, so for Q1 and Q5, the electric field is going to go, well, outwards, but specifically towards the origin. That's what we're really caring about here. The electric field towards the origin from Q1 and Q5 annihilate each other. They have the same magnitude, opposite direction, and so they will cancel each other out. So we don't need to worry about that. So E1 cancels E5 at the origin. Okay, now let's move on to Q2 and Q4. Okay, so Q4, again, the electric field is coming out. The part of the electric field coming toward the origin, so is going in this direction and is coming out in a fashion like that. Same thing with Q2. It's coming towards the origin and it's coming out like this. Now notice something about these two. I mean, yes, they're on angles, so we are going to have components. So let's say that we have X and Y directions. They both have X and Y components. So if we were to draw another dotted line to this horizontal line here, the X-axis, we can say that each of these are at an angle theta with respect to the X-axis. Now something you should immediately recognize is that the X components of these electric fields cancel each other out as well. And that's again due to the symmetry in the problem. So only the Y components stay, and we're going to end up adding them up. Okay, so now for Q3, the electric field, it's simply going to come straight down. Okay, so here we've got the electric field due to 2. Here we've got the electric field due to 4, and down here, the electric field due to 3. But remember, we said that E2x and E4x are going to cancel. Okay, so E2x cancels E4x. So the only contributing factor we really have to our electric field at the origin is the electric field due to charge 3 plus the electric field due to 2 in the Y direction plus the electric field due to 4 in the Y direction. Now, due to some more symmetry in the problem, since all the charges have the same value, E2y and E4y are going to be the same. Their y's are going in the same direction. They're both going down. Okay, so the size Q is the same and their distance from the origin is the same. So we can actually simplify this to E3 plus 2 E2y. Now I could have said 2 E4y. I just decided to pick E2y. Okay, now the formula for electric field is KQ over R squared. So for E3, it's going to be KQ3 over R3 squared plus 2. Now E2 is KQ2 over R2 squared. And the fact that it's the Y component, it's going to be this, E2y. Okay, now because that's a right angle triangle, E2y will be the hypotenuse, E2 times the sine of the angle. Okay, so here's E2 times the sine of the angle theta. Okay, now because I have a circle, okay, so this here would be my R4, this would be my R2, this would be my R3. And notice that in all of these cases, R2, R3, R4, all of them are the radius of this circle. Okay, so they're all the same. So in fact, R3 and R2 are the same. And also Q2 and Q3 are the same. The same thing in the formula because they're the same magnitude. So what we're going to actually do is factor KQ over R squared out. Okay, and I'm actually going to plug it in now that I'm factoring it out. So K is 8.99 times 10 to the 9 Newton meters squared per coulomb squared. Okay, my charge is 7.4 coulombs. divided by the distance squared. The radius is 2.2 meters. Remember that has to get squared. And in brackets, if I divide it out of the first term, I'm left with 1. And from the second term, I'm left with 2 sine theta. Now, what's theta? Okay, theta is this angle right here. Well, if we're dealing with, well, the symmetry we have here, the Q3, Q4, Q5, yes, everything here is equally spaced out. So that means that Q4 is exactly in between Q3 and Q5, or Q2 is exactly halfway between Q1 and Q3, making this angle theta 45 degrees. So I'm going to write that down there. Okay. Now, if you crunch all this out into your calculator, you're going to end up with an electric field value of 3.3 times 10 to the 10 newtons per coulomb. Now, of course, electric field is a vector, so we must include a direction with this. The net electric field is going down, remember, because due to the symmetry of the problem, all the x components cancel each other out. So that's what we were calculating. So that's it for this video, guys. If you enjoyed it, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me. Stay tuned tomorrow at 12 noon for video 159, Potential Difference and Electric Potential 1. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Whoop, whoop. Holy crap, my nose looks big on camera.